All right, welcome to week 4, I guess. Day 1, IS50B. Today we're going to be talking about the rasterization pipeline. So there's two main ways that you can draw a picture on a screen, like you got a video game, you got a person in a tree or something, you know. There's just two main ways that we do this. The first is called ray tracing, right? So with ray tracing, basically for each pixel on the screen, what you do is you shoot a ray into there, you see what it hits, and you draw that color. So if you have a green tree, you shoot a ray after ray after ray, and you know these things can, if they're reflective, they can bounce around and stuff like that. That's not what we're going to be talking about today. We're not going to be doing ray tracing today. We're going to be doing rasterization. Okay. Have you guys heard this term before? Rasterizing something?
I've heard of it, but I never knew what it was.
Okay.
Yeah, I can't say I'd be able to just define it.
Okay. So let's say that you've got a couple triangles in the world, and the red one is in front of the blue one, right? As far as, you know, perspective from the camera, or the galaxy colored one, right? It'll look something like this, right? The red one will draw in front of the other one. So there's something called the rasterization pipeline, and describe the rasterization pipeline is a common question for, like, you know, job interviews and things like that. So let's take it from the top and just kind of run through the rasterization pipeline, so you kind of have a high level understanding of like the steps that take place in putting things on the screen. And what this means is basically if you've got a bunch of triangles in your world, you're gonna, to raster means to sort of fill in the triangles on the screen and to have the colors match the color of the triangle or the texture or whatever. So it works something like this. All right. So let's say you've got a mesh, and the first thing you do is you are going to you're going to clip the mesh. Okay. So let's say you've got these triangles over here. Maybe there's a triangle like over here. This is off the screen, right? So anything off the screen gets discarded. All right. If you've got all these triangles like that are all like outside of the camera angle, all of these are going to be clipped away. They're going to be discarded. Things that are on the screen are cool, and things that are partly on the screen, let's draw it like half in white and half purple. It'll draw the part that is on the screen, and it's going to clip the triangle. Do you understand what I mean by clipping? So like if you've got a triangle here, it's going to make a new triangle essentially from like here to here and draw that part, and the rest of this is going to get discarded. So you've got something called a view frustrum. Let's take a top down. Here's the camera, and it's looking out this way and this way. This is your field of view, right? FOV. You guys know about FOV settings in video games and things like that? Christian?
Yeah.
Yep.
Yeah, so like your default FOV is 90 degrees, you know, just make math easy, but you know, if you're doing a video game for the console, oftentimes you have a narrower FOV because people sit back from the TV a little more. Whereas with a computer game, like you know, here I'm sitting, you know, here. Whereas when you're looking at a TV on your, you know, 6 feet away from your sofa, it has a little bit of a narrower FOV. So the width of this view frustrum is it's called a view frustrum, and it's got something called the near clipping plane. And then it's got the left clipping plane, the right clipping plane, and it's got a far clipping plane. And if a triangle is outside of this view frustrum, it gets discarded. And it's actually pretty easy to tell if something is within this. If you were to look at this view frustum from kind of the side, it actually looks like a pyramid. If I can draw this well enough, it looks like a pyramid with the top chopped off, because this it doesn't go all the way back to the camera. You want to have a near clipping plane, because if you don't, um, if you have a leaf or something that like covers, if there's like 1 pixel of leaf right in front of the camera, it'll occlude the entire screen, and it'll look really terrible. And also, like, the math gets really wonky when you go to 0, right? So you typically will have a near clipping plane. So anything closer than this, which might just be like, I don't know, 5 centimeters or something, like some small distance, anything closer than that to the camera actually gets discarded. And then anything outside of the FOV gets discarded. Anything too far away gets discarded, and that causes pop-ins. So you have to be kind of careful with how far away this is. This is often a detail setting, right? In some games, where you can adjust how far away it draws geometry and things like that. So the better your graphics card, the further back you can push the far clipping plane rather, and you'll see mountains further and further away off in the distance. And so how this process works is actually pretty simple. For every triangle, you can create a circle that kind of bounds it, right? A bounding circle. You know how we've been talking about like acceleration structures, right? And so you can either use a circle or a rectangle to bound it. It's pretty easy to use a circle. And what you do is you only want to accept circles that are on the inside of the left, right, up, down, near, far, right? It's a pyramid, right? So there's a total of 6 sides. There's also, up and down that I can't draw here. So if the circle is inside of all 6 of these planes, then it's accepted and it's drawn. And you can actually do this very easily. What you do is you take the center point of the sphere, and you project it onto the plane like this, and you see if using the normal of the plane, using the dot product basically, and you see if the distance is positive or negative. If it's negative, it's on the back side. If the distance is positive, it's on the front side, and you check the radius to see if it's going to get like partially clipped or fully accepted or fully discarded. Okay. That makes sense? So if the distance away is like 10 and the radius of this is like 1, then this circle here is entirely in front of the plane. You guys with me on this? And you have to do this for all 6 of the planes. So you basically just have a circle, and there's just a very simple dot product that you do between the normal of the plane and the position of the thing to project it on top here. To project onto the plane, and then if the distance is positive, it's in front. If it's negative, like if you project this point here onto the plane, you'll get like a negative 10 or whatever. And if it's got a radius of 1, again, that's fully on the back side. This one's fully on the front side. But if you get something that's like 1 unit away and it's got a radius of 2, then that's going to get clipped, right? So then you have to like go onto the inside of the triangle and like figure out these points where you have to figure out the points where the line hits it, and then you make essentially another triangle there. So you turn 1 triangle into 2 and clip it. And so this happens every frame for every triangle in your world. The good news is, like, if either of these clipping things gives you a negative result that's bigger than the radius, you just discard the whole thing entirely. And it doesn't matter that it's in front of this one and in front of this one and in front of this one. If any of them give you a negative, you throw it away. But if it hits on the clipping plane, then you've got to clip the triangle and do a little bit of work sometime. Okay. Okay, so do you guys understand that?
Yeah.
Okay.
I was a bit confused at first, but yeah, that I'm all good now.
Okay. So yeah, so it's really easy. It's the math is quite simple on it. It's quite fast. You still don't want to have like trillions of triangles you have to process a second, because you have to do that that first pass removal. Even if these things are all off camera, if you're doing that first pass removal of them on a trillion triangles, it's going to take a long time. So you still have to be a little bit careful, and you still have to use various acceleration structures to, like if there's a lot of techniques that we can talk about to cut down on the first pass even on it, but let's not worry about that just yet. So we're going to clip it, and then we need to do backface culling. This is another thing, and so let's say that you say that a triangle drawn counterclockwise is facing you. 2 dots on the eye. Can you guys think about how you can figure out, what would you use, dot product or cross product, to figure out if a triangle is turning to the left or turning to the right? What would you use, Grante?
Like rotating or actually
like the dots. Turning? So if this is point 1, point 2, point 3, this is drawn counterclockwise. And if this is point 1 and point 2 and point 3, the points in the triangle are clockwise. And this actually matters.
Wouldn't that be the cross product?
Yeah, you'd use cross product. Yeah, you'd cross product two of the vectors. It doesn't matter which two, because the first two are clockwise. The last one's going to be clockwise also, right? And so what you do is you cross product them, and if you get a positive result, that means it's facing you. And this is convention. It's not a rule set in stone. I believe in OpenGL you can actually pick which one of these you use, but you just got to pick one and stick to it. And so what you can say is like a triangle that is facing you has a counterclockwise direction, and one that is facing away from you has a clockwise direction. And so here's the thing, you don't draw these. You guys understand? Like imagine you're looking at a regular like 6-sided die, right? These triangles, if they're facing you, you draw them, right? And you'd have it go 1, 2, 3, 1, 2, 3. It's a terrible one. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. I can't even draw anymore. Now watch what happens if I have a triangle that looks like this. Like let's just focus on this one right here. If it goes 1, 2, and 3 counterclockwise, if I rotate it so it's facing away from me, it would look like this, right? 1, 2, 3. We're looking at the back side of the triangle now, right? We took it and went like this. You guys see that? 1, 2, and 3 like this. Now it's facing away. Do you guys see that?
Yeah.
And so if it's facing away from us, we can't see it. Do you guys see that? There's 3 faces of this die that are all facing away from us, and we can't see it. Yeah? Do you guys see that? Like, these 3 faces of...
My brain is loading.
What's that? Your brain is loading?
My brain is, yeah.
Here, check it out. So, here's the front of this remote control, right? And let's say it's drawn 1, 2... It's mirrored 3.
I see.
So it's mirrored, counterclockwise, okay? It's counterclockwise drawn. If I rotate it this way, the points would now be drawn clockwise, but you can't see it because it's on the back side. If you have a solid object, if it's not just like a sheet of paper, but actually like a solid 3D object, you can never see the back side of it. You see that? You just see the front side of the new front. You see that? No matter how I rotate this thing, you can never see the backside of these surfaces, right? And so you can turn off backface culling if you want to have a triangle drawn. Like if it's just a sheet of paper, you might want to draw it either way. If it's drawn either way, but typically you're dealing with solid objects, and if you have a solid object, then if it's drawn clockwise, if it's drawn clockwise, like this, 1, 2, 3, you can't see it. And so backface culling, if everything facing away from you gets thrown away. Okay.
So what if you have a mirror, like behind an object, and you're looking at the front of the object, but the mirror is looking at the back of it?
Yeah. Typically, you will create, well, there's no typically. Like, reflections are annoying, right? If you... let's say the easiest way of doing it is you just make another camera facing out of the mirror, and you have it take a snapshot of the world. So you render the scene from its perspective, and you render that to a surface, and then you draw the surface with the camera on it. That's kind of the easiest way to explain it. The reality is, like, they'll do tricks with, like, warping an image and things like that. But if you think about it, the backside of this is visible from your perspective. It's not visible from my perspective, right? So if you have a camera, like this camera right here that I'm pointing at, from its perspective, these points are counterclockwise. From my perspective, they're clockwise. So I don't draw it from my camera, from my eye, but I would draw it from that camera there. Make sense?
That makes sense, yeah.
Yeah. You can never see the backside of an object. That's why if you ever play a video game and you accidentally get the camera inside of an object, it suddenly turns transparent from the inside. Have you guys ever seen that in a video game? Where, like, the camera moves inside of a tree or something?
Oh yeah.
Yeah.
And then all of a sudden you can see out of the tree, and it's like the tree's hollow, and you can just see out of it. Or a rock, you accidentally enter a rock, and you can just look out, and that's because of backface culling.
So, real quick, this is also useful because, like, for a cube, the other sides behind it are also not drawn because they're facing away from you. As in, not the inside, but the outside that's facing away.
Yeah, and that's how you know what's facing away from you. If you have a cube, there's 6 faces, or there's 2 triangles per face, right? So there's 12 triangles total in a cube. Only 6 of them can be visible at once, right?
Yeah.
And you know which ones are the ones that are visible because they're the ones that are drawn counterclockwise. If you ever rotate the cube, so now that's the backside. What was it? The points of the triangle that were drawn counterclockwise before are now drawn clockwise, and you don't draw them. So you always know what the front of a surface is and what's the back of a surface. And the back surfaces don't get drawn by default. You can turn that off. Like in OpenGL, you can disable backface culling if you want. But there's no need to if your meshes are properly lined out, in a specific order. And Blender and Maya and things like that will do it for you. Like, they will, when they save the meshes to disk, it's done very deliberately, so they're all drawn according to the same convention. Okay. And sometimes, though, that's backwards, and then you have to, when you like import it into Unreal Engine, you have to fix it. So you'll see the backside and not the front side, and so it looks really weird. It looks like when you're looking at the inside, it's like you're looking at this. When you see a cube and you rotate it, and you still just see the backside of it, and it's this really weird, trippy, psychedelic effect. And that's one of the reasons why you need to know all these things, because, like, sometimes it goes wrong, and not everybody uses the same conventions when you're, like, importing a mesh and things like that. So you need to hit a checkbox and have it import the other way, right? And we can look that up. I think probably Unreal Engine 4 backface culling. Okay, well, yeah. Okay, this is actually a great example of what we're talking about. So here's the camera, right? It's all these objects that are outside the field of view that get cold, right? So these guys get cold because they're on the backside of the right clipping plane, and these guys will get cold as well. And then anybody who is like on the line is going to get clipped. Okay, so scene view with only objects in the view frustum. Occluded objects are cold. Okay, yeah. So so what? So they're doing visibility culling, which I haven't talked about yet. And so what visibility culling is if one object blocks another object entirely, then they get discarded as well. So this guy is blocked by this one. This one's behind a wall. This one's behind a wall, right? Do you guys see that? And then testing visibility within an actor's bands. Bound scale, culling methods. Yeah, so this would be the bounds using a box and a sphere. These are various things which is visible. Bounding sphere is used for fast collision detection. More often, it's greater than the object contains. Bounding is closer to shape, where it's more accurate results. So remember how I was just telling you that there's like a bounding circle, right? Stover, Grante? There's a bounding circle that's used. Yeah, so there you go. You can see it for an object, right? And so if you can't see any of this circle here, well, it's a sphere, but if you can't see any of the circle here, then this statue can't be seen from anywhere, right? And if you want, you can use a sphere, or you can use this rectangular prism kind of thing here, and that allows you to very quickly discard things. And let's see, distance, max draw distance, that's for like the far clipping plane, and FOV, near clipping plane, far clipping plane, pre-computed visibility. That's what I was saying. There's a lot that can go into that, where you can cut down on the triangles that you have to process entirely. Come on, where is the backface culling? Backface. Okay, what's time on here at all? Okay. Still good. Anyways, had good photos of it. It's a bit odd that I'm getting these hits for backface culling without it actually being on the not actually being on the page. Okay, so yeah, here you go. So this is what I'm talking about. That's actually a great illustration. So if you have it backwards, this is what you will see. Do you see how like trippy that is? It's like it's almost
weird,
right? Because what you're seeing is the back faces being drawn and not the front ones. And so, like, if you had this red cup here, you would see the back part of the cup and not the front part of the cup. And as it rotates, it creates like almost this weird optical illusion of it rotating the opposite way, right? You see that? It's almost like it's rotating to the left, but what's actually happening, it's rotating to the right. There, see? So, blend mode mask, let's see. Two-sided. Yeah, so two-sided means draw the back faces as well. Yeah. And you have to do that sometimes if you're doing translucent, or maybe you do, I don't know. Okay, interesting. Neat. Yeah. So, yeah. So at least that kind of illustrates. Do you guys understand backface culling now?
Yeah, that makes sense.
Okay.
Yes.
So clipping the mesh, backface culling, and then you're gonna have your I guess I'm doing this in purple. Purple's not really readable, is it? Yeah, either way. Yeah, stick with consistency, I guess. Then you're going to have something called a Vertex Shader, which actually took place before that. But these are in no particular order. It's starting off with the pipeline. Let me... Rasterization Pipeline. So, yeah, the Vertex Shaders are actually going to take place prior to this. Yeah. Basically, you can write little programs. Did you guys do shaders in IS-50A? Do we mess with that?
Not that I remember.
Yeah, I sometimes do.
Yeah,
Sometimes
I don't think so.
So shaders are little programs that run on your GPU. So you can do things with Vertex shaders. What?
There it is.
You can do things with Vertex shaders. This is actually thanks, bro. Let's move this up here because this actually has to take place prior.
These came in.
Thanks, girl. Just put them off to the side. So shaders are programs that run on your GPU. So let's put up here. And there's actually a new shader that beyond Vertex, and there's geometry shaders now. That this must be an old image. It's fine. So a Vertex shader basically takes a vertex as an input. So a vertex comes in as input, and then you return a vertex as output. So if you pass in all the vertices of a cube as input, your shader can do things like move them. Right? So if you wanted to do like a cube of Jello, right? You can do that as a program running in your inside of your GPU. So you don't actually have to have your CPU handling any of that stuff. No pictures. Yeah, that's pretty good. Pretty good illustration there. So you take these vertices in, and then it runs through a shader, and you can move them around. So like you can do animations and there's a lot of cool special effects you can do with them. And then you're going to get a triangle, and then these things, and they've cut out the intervening steps here. And then rasterization means actually converting a triangle in like a 3D world and putting it into pixels on the screen. And then there's another shader that runs after that, after rasterization, where you take a point, a pixel as input. They used to be called pixel shaders. Now they're called fragment shaders because they don't necessarily correspond to pixels on the screen. You can think of this as a pixel shader if you'd like. I won't stop you. It basically takes a pixel as input and then returns a pixel as output. And so you can do all sorts of really, really interesting things with fragment shaders. Like there's just all sorts of neat special effects you can do with it. But let's talk more about the rasterization pipeline. Okay, so yeah, so you can do grass effects and things like that. You can have the grass blowing in the wind.
Who are you talking to?
I'm talking to my IS-50B class.
Your
So
son class?
I have long classes on Tuesday. So
Don't
so-
they read your smoothies?
no, that's all right. I'll have it later. Okay. So we've gone through the culling process, and at the end of the day, we know that something's going to get drawn. Now we're gonna rasterize it.
Daddy?
And rasterization means you take a point, and a point.
Daddy?
Yes, girl.
I want to make a video game with you.
You want to make a video game with me?
Yeah.
All right. That makes me very happy to hear. So, given a triangle, you are going to fill it with you're going to fill the pixels on the screen corresponding to that triangle on the screen. And so this first, before you can do this, you need to project it. So you need to project the triangle onto the screen. All right, so if you have a camera, let's go back up here. Let's say you have a triangle right here, right smack dab in the middle of the screen. This is going to have X, Y, and Z coordinates of like 1,972 and negative 9,073, right? Like these are going to be in what are called world space coordinates. And so when you project a triangle, you translate it. There's also local coordinates, which we'll ignore for now. From world coordinates, you're going to project them onto screen coordinates. And there's actually sometimes you project them into like this sort of idealized screen coordinates where it's like -1 to +1, like this. And then you project from that into the actual, you've got 0, 0 in the top right, and if you've got a 640 by 480 resolution, you're going to have 640 columns and 480 rows, and this triangle is going to correspond to these locations right here. So do you guys understand that? And this is a matrix multiply. So your camera is going to have a matrix that basically corresponds almost exactly to its location in the world. Like if you actually look at a projection transform, you can actually understand it. It's, I think, the inverse of like the of what it takes to get the camera to get to that location. And so what you do is you just take the point in world space, you do a matrix multiply where you've got your camera transform, and you got the X, Y, and Z of the point. So you got the point in space, you got the projection matrix whose values don't matter, and this will end up with a screen space coordinate. Again, sometimes you project it to an idealized screen coordinates. Sometimes, at some point, it's going to end up telling you, well, this is at point, row 500 and column 20 or whatever. All right? Does that make sense to you guys?
Yeah. So initially they had to make it so that anything can, for the most part, be displayed on any screen. Like, is that the whole thing with component, VGA, and HDMI, that they're all supporting? I know it's a different class topic, but
so how it actually goes out of your video card, right now it doesn't matter. There's going to be something that we're talking about here called the screen buffer, right? Which is, at the end of the day, your graphics card is going to have a chunk of RAM that holds red, green, and blue values, and those values get shipped off to your screen right now. And so if your monitor is at 640 by 480 resolution, at some point you're going to have this 2D array, and it's going to have this value here is 0, 0, 0. It's pitch black. This point here is fully red, fully blue, no green. It's perfectly purple, right? And after you finish rasterizing, you say, all right, I'm done, and you push that frame out to your monitor. And how quickly you can push those frames out to the monitor is your frame rate. So all these things, drawing all these triangles, all this rasterization, all this clipping takes time, right? And you still have to do the AI for your game and handle mouse and keyboard handlers and all that stuff, and play sounds. All that stuff eats into the time that it takes before you can put pixels on the screen. So you want this whole process to be as fast as possible. And so the rasterization process is the process through which, let's just say this is a perfectly purple triangle. You sit there, and for every pixel within that triangle, you draw a pixel, a purple pixel to the screen. And so it's filling the triangle. Okay? So, do you guys understand that? And this is a word you need to know, because if you just, I don't know, if you go into a job interview and you're like, what's rasterization?
What?
They're not gonna.
What's rasterization?
What is rasterization, Ada?
What is it?
So,
just as...
Here. So you figure out where the triangle is on the screen, and this is a triangle that has a red corner, a blue corner, and a green corner.
It's getting out of the box, though.
And so it's going to fill every pixel that's within the triangle is going to get filled with a color that's sort of an average of the three colors based on how close it is. And if it's texturized, then these points will be pulled from a texture, which is just a 2D image. And there's something called UV mapping that tells the engine what part of the picture corresponds to what part of the triangle. And so you select from the picture these parts of the image, and as you go through and rasterize, it pulls the corresponding points out of the texture and draws them on the screen. Okay.
So in principle, a 2D game will pretty much always run faster than a 3D game?
Yeah. It's a lot easier because you don't have to do a lot of this stuff. And that's why, like, back in the day, like, you know, every game was 2D because you don't have to do a matrix transform on everything. You don't have to do all these projections and culls and things like that. If you have, like, a Super Mario World, you have a tile-based system where each thing on the screen is a sprite. A sprite is like a 2D image, right? Like this. And so, if you wanted to make Super Mario Brothers, you would have a bunch of sprites, and as Mario animates around, you'd see as he's turning and things like that. Large Mario, small Mario. Basically, you just, for every tile on the screen, you copy. It's a very fast copy that copies the sprite for, like, the star or whatever from memory onto the screen, and that's how 2D games worked for a long time. Is that you would have the game itself would have basically just a tile-based system saying at this location there's a brick, and at this location there's a pipe, and when you're on screen you just read that section of RAM, right? So, like, it's all probably laid out in such a way that all the stuff is next to each other in RAM, and you just grab, as you move to the right, all you have to do is read the next column worth of data and then draw those things on the screen. And then as you move, you can actually tell it to scroll sometimes, depending on the hardware. Tell it to move everything so that you don't have to constantly be drawing it to the screen, to the hardware. And so that's, you know, it doesn't have to go through any of this mess of rasterization. That's why you didn't see 3D games really appearing until, you know, 90, 95, 96, somewhere around there. Because you know, this process of rasterization is hard. And you have to do this for every pixel on the screen here. Like, for every pixel within the triangle, you have to go through and you have to do a computation. And that computation is how far am I away from so color or texture. So for every pixel within this triangle, yes, girl.
Are lifeguards like those people who dress in, like, red and watch over pools?
That's a lifeguard.
Are there land lifeguards, or are lifeguards only for water?
They're for water, yeah. And so if you wanted to figure out what the color should be here, like, it should probably be white, right? Because it's about equidistant from all three of the points. Then for every point within the triangle, like, you know, this triangle might have, you know, 1,000 points, 1,000 pixels within it. It has to do this computation where it figures out how far away the point is from each of the three corners, and the closer it is to one of the corners, the more that color it gets. And so that's an amazing amount of math that needs to be done, right? Which is why if you look at, like, early video games, they don't do this. They don't have color interpolation. They don't have texturing. Texturing is even later, really. If you look at, like, Battlezone, like, going way back in the day, they don't even rasterize at all, right? So that's, do you see the difference here? They're doing line.
That's awesome.
They're doing line rasterization, but they're not filling the triangles, right? So they do line rasterization, which is easier, right? Because there's less pixels you have to put on the screen, right? And this was a game that was like early 80s, I think.
What's that?
This is Battlezone. It's like one of the first 3D games.
Can you play that video?
I don't want to get a copyright strike.
What's a copyright strike?
YouTube gets mad at me for doing it.
How come it's going to get mad at you?
They don't want you showing other people's videos or whatever.
Why?
There we go. So yeah, so check it out. So when did this game come out? 1980. Wow, 1980. Look at that. 1980. It's impressive.
Was it a PC game?
It was an arcade game.
Arcade game. Okay.
Yeah. And so 1980. That's earlier than I thought. And so you can see the guy here controlling it, and he's staring into like it looks like a little periscope that you're looking into, which was kind of a cool design because that's like a tank, thing, like you're looking in the periscope. So it had this cool design. I don't know what would happen if you were short though. And so it did wireframe graphics, right? Where it doesn't fill the triangles. And so they would just kind of like when they did the rasterization, they would just do a line raster and just draw the lines. And so for that, you only draw the pixels corresponding to the lines like this. And that is going to be your next homework assignment. So given a point and a point and a point, you're going to draw all the pixels between them. Okay? So you're entering the 1980s now. All right?
Sweet. Will this be on the main server?
It'll be on the main server, yeah. And it's gonna look something like this. Click, clicky click, clicky click, clicky click, and it line rasters. Okay.
Aww.
You like that, girl?
Can I try?
Click,
Okay, alright then.
click.
Can I try?
Yeah, sure. Go for it.
I'm quite excited for this.
Yeah. So you have to figure out how to draw a line. There's various algorithms for it. And then you can keep clicking if you'd like. This is mouse support within a terminal, by the way. You're doing some line art here. I don't know how this is going to
The
look.
putty devs are screaming.
The putty devs are like, "What are you doing? Why are you doing Battlezone inside of putty?" I don't know what this is going to do actually.
Okay,
Hit return. Hit enter. Okay.
What in the world?
Yep.
Beautiful bow.
Yeah.
I
Nice.
made a bow. That's not intentional.
Is that what you wanted?
No.
No?
No. How
Well,
do I? Can I
don't-
have another dot?
No, it's too late now.
No.
But that's what you guys are doing. And so you can see that this algorithm is very chunky. It doesn't look very good. There's no anti-aliasing. But like the basic things you should think about when you start is like how do you draw a horizontal line, right? That's one thing to think about. That's maybe easy. And then another question is like how do you draw a vertical line? And how do you draw a line at 45 degrees? And the algorithm I'm using is very simplistic. Like it's not super good. So just think about that though. And just when you're done with it, I'll just look at your code manually and grade it by hand. You guys don't need to do the red rising unless I don't know. I don't know if you guys want to do the red rising game review. But
I don't mind. I added it to my game list because it's actually really fun.
yeah, a lot of thinking, and it's a fast game too, which a lot of people like. I like longer games. I like games that run for like hours, but
Yeah, same.
you do. Okay. Okay.
How come you're interested in Super Mario Brothers then?
They were asking about 2D games, and so 2D games, the process is different. Like they don't go through this whole nonsense here, because when you have a triangle, If you want to save time, you just do a line, right? You know what I mean? Like these are less points you got to process. Okay, so after you've done all this, and you have to do color interpolation, and then with textures, for every point within the triangle, you've got like some picture on disk, right? Let me draw some bricks or something here. Basically, you would map the triangle. Let's see if I can do this correctly. Green and blue and red. And so you do what's called UV mapping, like this, and this would be 0, 0, 1, 0, 1, 1, depending on the coordinate system. And then when you were like, all right, what pixel goes here, that's going to grab it from this point right here. Do you guys see that? And if I grab that point there, that's going to grab from the picture right here. You guys understand? That's how textures work.
That makes sense.
Yeah. So every point on here is going to be like, hey, I correspond to that point in the picture. I correspond to that point in the picture. I correspond to that point in the picture. And then as you go through and you're rasterizing, which means filling the triangle, you're pulling these points over and over again from disk, or it's going to be in RAM. You don't want to be pulling it from disk. Then you're not done yet. There's one more step. We got 4 minutes left. Step 5, I don't know. You can't really count the steps, I guess. But then you've got what's called Z buffering. And Z buffering says, what happens if you draw one triangle over another triangle? Which one gets drawn? If there's a triangle a meter away from you, and the exact same triangle, which would be bigger, 2 meters away from you, but they correspond to the exact same screen coordinates, right? Because something further away is bigger, it gets projected down to the same number of pixels. Let's say you have the exact same triangles, except one's green, one's red. The green one's closer, the red one's further away. Which one gets drawn on the screen? Like if I have a green triangle here, and then a green triangle here, which one gets drawn? Or sorry, a green triangle here and a red triangle here, which one gets drawn?
I hope the green, right?
The green, yeah. The near, draw the near pixel. That's what Z buffering is all about. So for every point on the screen, you got your screen buffer, which has like all the output, the red, the greens, the blues, that are actually going to get sent to the monitor. You've also got something called a Z buffer, or a depth buffer, which holds how far away it is. So if you have a triangle here, and this one, let's say that all the coordinates are at -5, just to make it easy, and then you draw another triangle that's at -10. Each point on here is going to be -5 away, right? And so in the depth buffer, you hold -5, -5, -5, -5, -5, all over the place, and then you try overdrawing it. So you try drawing another triangle on top of it. The one that you keep is the one that is closer to the camera. So if one is 5 away, one is 10 away, you keep the one that's 5 away. But if part of that triangle is 1 away, then the ones that are 1 away will draw in front of the one that's 5 away, and the 5 away ones will draw in front of the ones that are 10 away. And so for every pixel, you have to do a depth buffer test, or a Z buffer test. And so what will happen is that you'll end up having one triangle, let's say this guy's at -10, he's 10 away from us. All these pixels, which are at -5, will stay as, the green one was the near one. So the green pixels will stay, and then the red pixels will not draw. So it's rasterizing all these red pixels. When it comes to draw it here, it has to do a depth buffer check. Who's closer, the green pixel at 5, the red pixel at 10? Oh, the green pixel at 5 is closer, keep it. But then out here, there's nothing there, so it draws all those red pixels in. And so this is a very elegant solution. The only trouble is, like, if you keep drawing triangles over and over onto the same spot, you're going to very quickly run out of your draw rate. You know what I mean? Like, if you keep drawing triangles on top of each other and they keep overdrawing each other, then your graphics card is going to run out of pixels per second. You guys understand? So a little bit of overdraw is okay and probably inevitable, but in general, if you have a massive amount of overdraw, then your engine needs to get good. like we saw with the like we saw with the UE4 picture there, what your engine itself needs to figure out, like, okay, this sphere here is being blocked by these two guys, so don't draw it at all. That way you reduce the overdraw. There's still probably going to be some overdraw on these pixels right here. You guys see that? It's like this guy might be like 5 away, this guy might be 10 away. They're both going to project to the same screen coordinate. You guys understand?
Yeah.
Yeah.
Yeah, so there's probably always going to be some overdraw. That's okay, you know. But if you have like 900 objects back behind here, you would keep drawing to the same location over and over again, and you'd be like, oh, -5's closer than -10, and -5's closer than -15, and -5's closer than -20, and you just, all those things will keep drawing. It'll keep doing the rasterization process, which is, you know, somewhat expensive, right? Because you got to go through every pixel in the triangle and draw it to the screen, and for each pixel you're drawing to the screen, you have to see which one's closer, and you're going to keep drawing and drawing and drawing and drawing, and none of it will make any difference once you've got the near one on the screen. So a little bit's okay, but in general, that's an issue for like your engine to do. And there's some really interesting occlusion culling algorithms. Like, yeah, check this out. Like, it's pretty cool. So you got a camera here, and you got all these cities, buildings, and some of them are blocking other buildings, right? And so figuring out an automatic way of doing that is interesting. Yeah, view Frustrum. Yeah, okay, that's what we're talking about here. Yeah, backfaced triangles don't get drawn. Things that are outside of the view Frustrum get culled. Things that can't be seen get culled. And if there is some overdraw, like right here, this part and this part are going to probably project to the same point on the screen. And so then you'll allow the depth buffer to handle that. And then you're basically done at that point. There's things called pixel shaders, which in addition to texturing, well, you know, sort of as an alternative, let's put it as another step 4. You can either color it or texture it or use a pixel shader. Pixel shaders oftentimes grab textures. You can run a program. And so rather than just a simple texture lookup, which is how things worked back in the late 90s, early 2000s, nowadays all of this, rather than coloring or texturing, it runs a program. And so your GPU has like lots and lots and lots of little CPUs inside of them. And those CPUs understand very simple things, and they run the same program in lockstep with each other. So all the pixels, shaders, like all these compute units inside of your graphics card are all running essentially the same pixel shader. They got, well, not all of them, but like a whole bunch of them will run all at the same time and run at the same time. And each one is like handed a different pixel. And then it runs the program on it. And you can do all sorts of really interesting things with pixel shaders. It's ridiculously impressive, like if you see what people do with these things. But it's basically just a program. It's a program that takes a location. So it takes a location as input, and it returns a color as output. That's what a pixel shader is. You pass in a row and a column. You know, you're at this pixel right here, and then it's going to return to you, that should be this color. That's all a pixel shader does. It takes a location as input, returns the color as output, and each of those is going to run, like, you know, on every point on the screen, basically. And that's basically it. That's kind of the high level view of like how like rasterization works. Let me see if I forgot any. See if I forgot any of the steps. I'm just doing this off the top of my head. Vertex Shader geometry. Yeah, that's what I was telling you guys. There's these things called geometry shaders now that will actually generate geometry for you. It's pretty cool.
Daddy, we need to go.
Okay. They clip geometry off the screen. Then it gets projected to the screen. It then does the rasterization process of filling in the pixels, right? So you get your guys here, you fill it in with pixels. You run a pixel shader on it, which it runs a program that produces the colors, and then it goes through the Z buffer. And there's also stencils, so you can like stencil out part of the screen and only have part of the screen drawable. So you can have like there's all sorts of cool effects you can do with that as well. And that's it. That's how a frame is made. So in one lecture, I think you guys kind of understand now how you go from like you got your stuff in Unreal Engine. Move your foot, girl. With XYZ locations and things like that in Unreal Engine to having an actual thing drawn on the screen, and you do that fast enough and gives you the illusion of motion. You got a video game. Okay. Any questions about this? Girl.
I go ahead. I just need to look over it a bit more to completely grasp it, but it looks good.
It looks good. Yeah, it's there's a lot of steps. There's a lot of steps to it, but they're all pretty straightforward. Like when you get into it, like this like projection thing. Like if you look at the math, it looks like horrible, and then you just understand that it's just like we talked about transformation matrices in 58, right? Like the math into like rotation and translation. Yeah, it's just one of those, and then all the points in the world get translated through that projection matrix, and it's like each step's not bad. So your job is just to do line rasterization. Okay, I know we gotta go. Let's go. Okay, so you guys given a line, draw pixels on the screen, and that's it. You guys got a week. All right, peace out, you guys.
Yeah, sounds good.
Yeah, thank you.
Bye.